Hi, welcome back to Statics 1. Today we're going to be talking about the centroids of areas made up of composite bodies. So what do we mean by that? Let me start with reviewing a little bit, talking about centroids. And we did say that X bar, which would be the centroid with respect to the in the X direction, is equal to, it's simply an integral, double integral of x dx dy over some area. The area could be like the cross section of a beam. It could be a rectangular beam. We'll do the integral over that area, and that would, depending on the dimensions here, we would set the limits of our integral. I haven't finished, of course. Divided by double integral of dx dy, and of course the integral of double integral of dx dy is simply the area of our member that we're evaluating. So if we look at this, we realize that x bar times the area equals simply this moment arm x dx and we're going to use that in a minute. And we can do the same thing in the y direction. So y bar times a equals the integral of y dy dx. Okay, we're going to come back. We're going to use that. So I didn't get to our composite areas. Got a little distracted. But the centroid of a rectangle, for example, is simply the center. So x bar would be equal to, if this were, typically we use B is the width, H as the height, and the X bar would simply be B over 2, and the Y bar would be H over 2. That would be relative to, obviously, the lower left corner. Y bar equals H over 2, and we could do this formally by actually evaluating this integral. I think we might have done it, I can't remember. And we can do the same thing for a triangle, and for, I'm going to draw a sort of arbitrary triangle, and if we knew the coordinates of the corners, in other words, if we knew the coordinates of that corner as x1, y1, and this one were x2, y2, and this one were x3, y3. And the centroid in the x direction is simply the average of the x values at each of the corners. So x bar is simply going to be x1 plus x2 plus x3 over 3. And y bar equals y1 plus y2, y3 over 3. Okay, all this is review so far. So now what we're going to talk about are composite areas. So a composite area could consist of anything that's a combination of, usually it's typically combinations of simpler areas for which the evaluation of the centroid is a relatively trivial task, such as x bar equals b over 2 or y bar equals h over 2, or taking the average. So you could evaluate, we're going to show you how to evaluate, for instance, the centroid of what you might think of as complex shapes. And we could do this formally using this kind of an integral, or what I'm going to show you in an instant is a simpler way of doing that, which takes advantage of this relationship. All right, so how do we do that? Now I'm going to set my coordinates here. And I don't know if I mentioned this before, but if you have a symmetric object, obviously this one is asymmetric with respect to y because it's shorter. This bottom flange is shorter than the top flange. However, it's symmetric about the y-axis. In other words, if we were to hold a mirror up here, it would essentially look the same on that side as it does on the other side. In that instance, we should automatically know. If you haven't figured this out already, you can do this using formally doing it that way. But our x bar in this instance equals essentially the center of this thing. And if we made our coordinates, imagine that our coordinate system is like this. That's y. That's x. Our x bar would be equal to 0. Okay, so we're only interested in this particular case with what y bar is. What is the centroid of y? And it's really important because it's going to tell us where that, when you have bending in this thing, it's going to tell us where we have a elevation relative to the bottom, where we have 0 compressive or tensile stresses. All right, so let's see if we can figure out how to do that. I'm going to use this relationship I've written for y bar. So I'll rewrite it here. Y bar equals that double integral of y dy dx over double integral of dx dy. Oops, got that wrong. Dx dy. And what you might realize is that integrals are just like summations. You're just summing over like very small areas. So if we're going to do this kind of a summation, this integral over these 3 areas, like let's say we were to divide this into 3 parts, and I'll do it by using purple. I don't know if this is going to work. No, maybe. So that's one part. I'll use red for the upper one. So what we're going to do is break it into this part, and this part. And we can do that basically by writing this integral 3 times. Or we can actually use the summation sign, which is the way I'm going to do it, which will save me a little bit of writing. So you can say y bar equals the summation of that double integral, y dy dx, over, again, we can make a summation here of integral dx dy. So this will go from I equals 1 to n, where n is the number of composite components of our overall area. So there'd be 1, 2, in this case we'd have 3 composite areas. But I'll just, in general, I'll put an n value there. And I'll do the same here. I equals 1 to n. And this would be integrated over, I'll just put it I here, implying that the limits are dependent on which rectangle you're doing this for. All right, so what can we look, when we look at this, we realize we're only dealing with rectangles. We know these centroids of rectangles. And we also have this very handy little relationship here, which shows us that numerator over there is just equal to y bar. In other words, the centroid of the individual rectangle and the area of that rectangle. So I'm going to use that relationship here. So we're going to have a summation of y I centroid. So in other words, we have the centroid of that, each one of those components times its area. And then in the bottom here, this relationship, the double integral of dx dy is simply the area. So we have the summation of an area. Okay, so this is really easy. Now we can do this very easily. We know how to find yi. In other words, I'm sorry, we know how to find the centroid of each one of these pieces. It's simply the center here. And they're always, make sure you always measure it relative to the same origin location. So if we have our origin down here, our y value here will be just h over 2 of this rectangle. And then this one will be measured, I'll write it in here. So this is 1, this is 2, this is 3. So I make rectangle 1 the bottom one, rectangle 2 the middle, rectangle 3 the third one. We can measure our value of our centroid like that. So there's our centroid 1. It's basically halfway up from the bottom. Halfway meaning halfway relative to the thickness of this. And then Y2, I'll write it over here. Y2 is the distance from the bottom to the middle of our intermediate or middle rectangle. And then Y3 would be, then from that same point up here, that would be our, Y3. And of course we need to remember these are centroids, so I'm going to put a little bar here. Right, and so that would go from the bottom up to the middle of our third rectangle. So that's simply how you do it. It's a very easy technique. So you'll just be entering yi, ai, and then for y1, a1 plus y2, a2 plus y3, a3, and then adding up the areas, and that'll give you your y centroid. So I'm going to show you a quick example. Based on this geometry, I'm going to add some dimensions on here, and then we'll evaluate this. And typically, the way you do it, the way it's done in the textbook, is they set up a table of values of yi, the centroid of each of the components, the areas of each components, and then they add them up. And well, I'll show you how you do it. So what are the dimensions of this thing? We're going to make this 150 millimeters. Okay, the middle rectangle is going to be 150 millimeters high. This top one is going to be 150 millimeters across. And the bottom one is going to be 100 millimeters. How am I going to do this? Put it right in the middle. 100. All right, so the bottom one is 100 millimeters across. And they're all the components are all 15 millimeters thick. So I will write that in, it's getting a little messy, but I'll write it here. 15, here, 15. Do it like that. 15 millimeters. That's mm there, sorry. And we have 15 millimeters here. And the bottom one is 15 millimeters high. How am I going to do that? I wish I had a little CAD operator that could help me out here. But we'll do it like this. 15. Alright. I wrote it over here. 15 millimeters. That's the bottom one. Alright, so now I'm going to create my table that we're going to use to evaluate this the centroid, y centroid. We create a table, and over here we number the rectangle segments. And we're going to use this rectangle 1, rectangle 2, rectangle 3. This refers to our rectangle components, rectangle 1, rectangle 2, rectangle 3. Right, rectangle 1, 2, and 3. And we're going to measure the centroid from the bottom. So we want the overall centroid of the entire area as opposed to the centroids of the individual pieces. I'm going to put that over here. We don't know exactly how high it goes, but it's somewhere here. Sometimes, and I noticed, for example, this problem is in the textbook, and they actually evaluate, they do something weird where they say, well, what is a y bar relative to the upper, this point here? In other words, measuring y bar down. You can do it either way. If you want y bar from the top and you're getting it from the bottom, you'll just subtract the total height from this height, and that'll give you y bar measured relative to the upper surface. But we'll do it this way. All right, so over here we're going to put in, first we'll put in our y centroid values. So we're going to put in here the centroids of 1, 2, and 3. We're going to put the area of 1, 2, and 3. Here we're going to put y bar A, so we're going to multiply the two, write that here. And the bottom here, we're going to sum that up. We're going to sum that up, which is exactly what we see over here. And if we sum those two up and divide them, we're going to get y bar. Okay, so let's do that. So what is 1? 1 is basically from halfway up of this 15 millimeter thick segment. So the centroid is 7.5 millimeters. And I'll write here millimeters. And over here I'm going to write millimeters. That's an m squared. And so what's this one going to be? Millimeters cubed. Right? Because y is in units of millimeters. A is going to be in units of millimeters squared. So we end up with millimeters cubed. All right, so that was y. Let's do this, all the centroids first. So the centroid here is going to be halfway up. This was 150, so halfway up is 75. But because we're measuring it relative to the bottom, we have to add 75 and 15, which is that height, which I'll write it, I'll do it just to be a little bit. 15 equals 90. Just so you, in case you're looking at there, you're going like, well, how did he get 90? But 90 is the number. That's essentially this centroid of the second one. Here it is, y2, relative to the center. Now how about this third one? So now we're going to add up 15 plus 150, which is 165. Then I need to add another 7.5. So we're going to get 170, 172.5. You can check me, make sure I'm right. And I won't add it, I won't write those, well I will write it. So it's 15 plus 150 plus 7.5. 7.5 is 15 over 2. And 165, 172.5. Alright, so that's it. Now how about the areas? This area is 100 times 15, so it's going to be 1500. That's our area 1, 1500. The second one is 15 by 150, which is 2250. You can check it. Make sure it's right. And the third one is, it has the same area. It's also 150 by 15. So that one is also 2250. And of course we would multiply these using our calculator, but I'm going to just write them down, the numbers, because I've already done that. We have 11,250, 202,500, and the third one is 388,125. And these, so now we're going to find the summation of A and the summation of y bar A. This one happens to be 6,000. And that one over there is 601,875. 601,875. So we're going to evaluate this now. We're going to evaluate y bar equals the sum of ya over the sum of A. And we're going to get y bar equal to 875 cubed over 6. So we have 601,875 millimeters cubed over 6,000 millimeters squared. So I like that. We get millimeters cubed over millimeters squared. We can do it. We can cross that out and we can say that's 1. So we have just millimeters to the first part, and that in fact is what we want to see because y bar is just a distance. So we're going to divide these 601,875 by 6,000. We're going to get 100.3 millimeters. Okay, so that's the centroid. of our composite area made up of this essentially the cross section of an I-beam. It's asymmetric. I don't know if it's called an I-beam. It's not exactly an I-beam, but a cross section of a steel beam, for example, with these dimensions, would have a centroid of 100.3, and you'll notice the overall dimensions are what, 30, 15, 15, 30, 150, 180. And this is slightly more than half of that 180 millimeters. And it makes sense because more of our mass is up here where we have a wider flange than at the bottom. Okay, so the response, this makes sense intuitively, and in fact it is the correct answer. So that's it. So this is for evaluating, and I'll write it down here so you remember this. The centroids of composite, I think in the book they say composite objects, but we're dealing only in 2D. They have some 3D problems we don't care about. Composite areas. So it's made up of multiple areas, each of which have simple enough geometry that we can readily evaluate both their centroids and areas. So if you have any questions, send me an email. Otherwise, I will see you in class next time.